I'm Unkit, and I'll be presenting my FIP on accelerating learned descriptor generation for visual localization. Navigation poses a significant challenge for autonomous vehicles. To be able to perform an effective traversal of its environment, the problem of localization, the process of determining the robot's precise position, is required to be solved. Traditional methods often rely on global positioning satellites, GPS, to retrieve precise positions. However, in scenarios such as indoor spaces or areas surrounded by tall buildings, GPS signals can often be degraded or lost. Hence, an alternative is needed. This is where simultaneous localization and mapping, or SLAM for short, comes in, and can be used to replace or enhance GPS navigation. An affordable way to implement SLAM is by using simple sensor configuration with either a monocular or stereo camera. This approach is called Visual SLAM or VSLAM. VSLAM can be categorized into two main types, feature-based and direct, though this report will only cover the feature-based method. Feature-based VSLAM uses feature detection algorithms to extract key points and generate the corresponding descriptor, with each pair composing a feature. A key point or interest point is a point in an image that can be used as a landmark that should be able to be detected regardless of distance and viewpoints. While descriptor is a feature vector used to represent a key point using information extracted from the image. Features can be matched in several images by comparing their descriptor to estimate the position and orientation of the camera. This can then be used to build a map of the environment. However, with recent growing appeal and success of artificial intelligence, there has been a surge in interest in combining the field of computer vision with AI. These emerging AI models aim to surpass traditional feature extractors such as oriented fast and rotated brief OP, which has been used by well-known VSLAM implementation OpSLAM3. One such contender is Superpoint. This model was trained on a dataset that consisted of simple geometric shapes, which were then further warped multiple times to train it on scenes from different viewpoints and scales. This resulted in a detector that not only performed well on synthetic datasets, but enables Superpoint to surpass or perform competitively with traditional handcrafted detectors like OP in the presence of imaging noise, illumination, or viewpoint changes. Despite the upsides of AI models, deploying them on embedded systems or devices can be problematic due to the trade-off between processing power and power consumption. These devices prioritizes low power consumption, often achieving this by limiting clock speeds. However, AI models typically benefit from faster processors to achieve better performance. While more complex AI models like Superpoint may struggle on such devices, those equipped with a graphics processing unit can or a GPU can offload these computationally intensive tasks onto it to increase performance, since GPU excel at executing massive parallel operations. This advantage is especially compounded for devices equipped with NVIDIA GPUs, such as NVIDIA Jetson, which can leverage the use of TensorRT to further offset the expected deficiency I mentioned previously. TensorRT is a high-performance deep learning inference library developed and designed by NVIDIA to optimize and accelerate inference for deep neural networks. TensorRT uses four main methods to optimize deep learning models. The first is precision calibration. TensorRT can deploy models in different precision computations, even if the model was initially trained in another, such as 32-bit floating point. TensorRT provides various precision computation, FP32, FP16, and INT8, where each has different effects on memory usage and performance. Notably, setting TensorRT to run the model in FP16 mode can lower data transfer time and improve performance via reduced computational costs but at the cost of reduced precision. Secondly, layer and tensor fusion. Here, TensorRT can further improve inference speed by merging layers of a neural network into a single unified layer, which reduces the number of memory accessors and decreases computational overhead. The third is automatic kernel tuning. Algorithms can be implemented in various ways. As such, TensorRT automatically selects the most performant algorithm implementation, called kernels, for a specific operation from a large library of kernels. These kernels are selected based on consideration like the type of hardware used, input data size, tensor layout, and other parameters, ensuring that the deployed model runs as fast as possible on the targeted device. And finally, multi-stream execution, where a CUDA stream is a sequence of operations that runs on a device, the GPU, that can be executed asynchronously and independently from the host device, and can even run concurrently with other streams. Thus, using streams can enable concurrency, which further improves code efficiency. Hence, TensorRT can be proposed as a significant way of addressing performance of running Superpoint on these low-power devices, especially since these devices lack physical hardware resources, and as such, an efficient usage of resources is paramount for them to maximize performance. This project aims to investigate the use of TensorRT with floating point 16 precision to determine whether it can accelerate learned feature extractor models, specifically Superpoint, to achieve a high-speed alternative to traditional feature extraction methods used in visual SLAM systems, particularly to run it on embedded devices. The following feature extraction algorithms will be tested. The baseline op implementation, Superpoint deployed using LibTorch, Superpoint using TensorRT with FP16 mode on. To evaluate the performance gains, the above two Superpoint algorithms are integrated into OpSLAM3, a well-known visual SLAM system. These implementations are run on a NVIDIA Jetson Xavier NX, an embedded device, with various metrics collected during the run. Computational speed is used to assess the speed-up gain from using Superpoint TensorRT algorithm compared to OP and Superpoint PyTorch, whereas accuracy differences between Superpoint TensorRT and Superpoint PyTorch are used to determine if there can be a potential loss in accuracy introduced by using reduced precision in TensorRT. To evaluate the effectiveness of the algorithms mentioned, a publicly accessible benchmarking tool, SlamBench, was used. SlamBench is designed as a standardized and verifiable way of comparing the different implementation of SLAM systems. It provides a quantitative evaluation of performance in terms of accuracy, speed, and more. Furthermore, SlamBench supports a broad range of datasets, useful for providing a comprehensive method of identifying the trade-off of each SLAM system. These two will be the primary method of evaluation, with any hyperparameters left to the default. SlamBench provides the following metrics: memory usage, main memory as well as GPU memory usage for each algorithm can be reported. This is necessary for determining the algorithm's effectiveness in terms of memory utilization, especially for embedded devices with limited available memory. Computational cost. This is measured using the time taken per frame for each algorithm, which is normally a good metric for how computationally expensive the algorithm is. The lower the frame time, the better the algorithm's performance. Algorithm accuracy. Accuracy is evaluated mainly using the absolute trajectory error, or ATE. Two trajectories, one from the ground truth and the other from the estimated trajectory of a camera, produced by an SLAM's implementation, are aligned together. The ATE is then calculated using the absolute differences between the two. This measures how well it matches the ground truth trajectory. And lastly, percentage of correct tracking. A way to measure the completeness of an algorithm is to measure how many frames were tracked and compare it against the total number of frames in the sequence. This will give an idea of how many frames were lost, either from tracking failure or used for initializations. The algorithms are tested on the below scenarios consisting of a total of 36 sequences. Baseline performance, these sequences are environment with free of significant disturbances, and such will be used as the baseline performance. Illumination changes. Some SLAM systems depend on the consistent lighting for mapping and may be negatively affected by unpredictable changes in brightness, be it natural or artificial. Thirdly, dynamic elements. Dynamic objects such as humans often move in the frame, which causes some SLAM system to suffer an increase in errors or performance. And lastly, fast camera movement. Fast camera movement often results in motion blur, which may disrupt feature detection and matching methods of many SLAM systems. And finally, the result. Across 36 benchmarks, each algorithm achieved the following average frame times in seconds. For OP, it achieved a 0.457. For Superpoint PyTorch, it achieved 0.415 seconds. And Superpoint with TensorRT, 0.185. Superpoint PyTorch is faster than OP by 1.1 time, which shows an advantage of using deep learning feature extractor over traditional extractors, despite the initial belief that it might run slower. However, the most substantial in performance gain is observed with Superpoint TensorRT, which achieved a 2.47 speedup when compared to OP, and a 2.24 times speedup when compared to Superpoint PyTorch. Superpoint using PyTorch showed only a small performance advantage compared to OP, but with TensorRT, the differences is increased significantly due to TensorRT internal optimization, use of floating point 16, and improved memory transfers. Thus, it can be concluded that TensorRT can be used to accelerate deep learning models such that it can surpass even traditional feature extractors in terms of speed. And with that, thank you.